Buckle up, everyone, because today we're taking a journey into one of the absolute most fascinating and, frankly, most extreme frontiers in the aviation world, the freezing skies over the North Pole. Welcome to this deep dive into polar flight operations. We're going to look behind the scenes at how aircraft fly over the very top of the world with absolute, flawless safety. Because flying over the poles, it's not just about following a line on a map, it's literally a monumental triumph of engineering that puts safety above all else against nature's harshest conditions. Let's decode exactly how they do it. Okay, let's dive into this. It's one of the most common questions passengers have. I actually saw a Reddit thread recently where someone asked exactly this. Why did my flight from California to Italy take me way up over Greenland instead of just flying straight across the Atlantic? And hey, it's a completely fair question. You're sitting there looking at that little screen on the seat back in front of you, and your plane is tracing this massive wide arc up toward the North Pole. It totally feels like you're taking the long way around, right? But in aviation, things don't work quite the way they look on a flat map. And this brilliantly illustrates why. The Earth isn't a flat piece of paper, it's a sphere. Those curved great circle routes you see on your screen, they are proof of that. On a globe, the absolute shortest distance between 2 points curving away from the equator is a great circle that arches toward the poles. So while it might look like a huge detour on a 2D map, flying over the North Pole is actually a massive shortcut. And this shortcut saves airlines hours of flight time and literally tons of jet fuel. That weird arc? It's mathematically the most perfect route possible. So here is our flight plan for today. First, we'll look at why we fly over the poles. Then we'll cover polar flight safety rules, fuel management in the freezing cold, communication and navigation challenges, and finally, how all of this comes together into a completely safe routine. Safety is the core of all of this, so let's get into it. Section 1. Why we fly over the poles. Now, taking these shortcuts from America to Asia or Europe is great, absolutely. But look closely here. The moment our aircraft crosses the 78th parallel north, we officially enter what the FAA defines as the North Polar Area of Operations. And let me tell you, this is a completely unforgiving, extremely isolated, and freezing environment. You can't just decide to fly through there on a whim. Airlines have to get highly specialized, incredibly strict approval from the FAA just to operate in this extreme zone. Section 2. Polar Flight Safety Rules. So the crucial point is this. We are not in standard airspace anymore, which means our equipment can't be standard either. The FAA mandates that any polar flight must carry specialized cold weather anti-exposure suits. Why? So that in the extremely rare event of an emergency landing, the crew can step outside and coordinate in minus 50-degree weather without freezing. On top of that, you've got to have expanded medical kits with automated external defibrillators, and fully functioning autothrottles are an absolute must. Every single detail is engineered for maximum safety. But what happens if something actually goes wrong and the plane needs to land? Is it just endless ice and snow down there? No way. You're looking at the Yakutsk Airport Terminal in Siberia. The FAA and Boeing have meticulously inspected multiple diversion airports across these icy regions. Before an airline even takes off, they must designate these alternate airports where they can safely land in any weather. And it's not just about touching down safely. Airlines must have a proven passenger recovery plan to get everyone off the plane, provide shelter and food, and extract them on another aircraft within 12 to 48 hours. Section 3. Fuel management in the freezing cold. Let's move on and see how this builds because it's a massive engineering challenge. Jet fuel doesn't just freeze into a solid block of ice at 0 degrees like water does. As it gets super cold, tiny wax crystals start forming in the fuel. The freezing point is technically the temperature where, if you warm the fuel up, those wax crystals completely disappear, usually around minus 40 to minus 47 degrees Celsius. But what's actually critical to keep those engines running is the pour point. That's the lowest temperature where the fuel can still physically flow. This pour point is about 6 degrees lower than the freezing point. Engineers rely on this 6-degree buffer as a vital safety margin, so the engines never, ever run dry. Now, what's really interesting about this is how modern aircraft actively manage the situation. They never leave it to chance. Notice that warning? You're seeing a fuel temp low alert triggered at minus 37 degrees. The system is designed to flash a yellow warning in the cockpit the moment the fuel temperature drops to within 3 degrees of the freezing point. This means pilots get alerted well before the fuel actually loses its flowability. And what do? They simply descend to a lower, warmer altitude, or they alter their course to find a warmer air mass. The aircraft tells you there's an issue way before it becomes a real danger. Section 4. Communication and Navigation Challenges. This quote right here from the FAA guidelines completely sums up the hidden dangers. In the polar region, magnetic heading is unreliable or totally useless for navigation. Just think about it. If you're flying directly over the North Pole, where exactly does your compass point? Every single direction is south. Magnetic fields up there shift so rapidly and are so wildly erratic that relying on a standard compass would literally be a disaster. But don't worry, aviation engineers solved this a long time ago. While regular compasses might lose their minds, polar flights switch to specialized routing systems based on true north instead of magnetic north. They navigate using satellites and the aircraft's own internal inertial reference units. Communication is another huge hurdle, because standard radios just don't reach, and solar flares can disrupt signals. To counter this, aircraft use a redundant, multi-layered network. They link up simultaneously via the high-frequency Arctic radio network and multiple SATCOM satellite data links. If one system goes down, another instantly takes its place, ensuring continuous communication with the ground. Section 5. A safe routine. When you combine all these rigorous steps, you get an utterly flawless safety record. The aviation industry doesn't guess when it comes to human lives. Before these cross-polar routes were even opened up for commercial flights, they conducted over 650 fully equipped demonstration flights over 2.5 years. What's more, looking at global flight data over the last 40 years, there hasn't been a single reported incident of an aircraft's fuel flow being restricted due to extreme cold on these routes. Thanks to monumental engineering, the hostile freezing atmosphere of the North Pole has been transformed into a flight path as safe and routine as driving down your local highway. So what does this all mean for us? Here's the thought I want to leave you with. Next time you're on a plane and you see your flight path drawing that wide, curved arc over the North Pole, you'll know it's not just a shortcut. Remember the incredible engineering keeping that fuel flowing at -50 degrees. Remember the redundant satellite links connecting you to the world and the meticulously planned safety havens waiting in the ice down below. Will you notice the immense engineering and safety protocols protecting you on your next flight? I truly hope this explainer has given you a whole new appreciation for the skies. Stay safe, and thanks for joining me.